Modulation basics. These are our topics that we're going to cover today. So we'll start with the introduction, some, popular modulation schemes and their geometric representations. How do we detect these symbols at the receiver side? And in terms of performance wise, we're going to show you some modulation spectra. Okay. So let's start with the modulation and demodulation. So this is the transmitter side and this is the receiver side. Left hand is transmitter, right hand is the receiver side. We have a data in that we want to transmit. Can be text, video, image, and so on. So first of all, we apply the baseband modulation to translate, bits to symbols. And then from there, we need to move this signal or information from baseband to the appropriate frequency band. If it's a Wi-Fi, it can be 2.4 gigahertz. If it's a, 3G or LTE, around 2 gigahertz band. So each technology has its frequency band. So we need to apply the carrier modulation to move this information from 0 hertz to the appropriate frequency band. Then once we are ready, we are going to radiate this signal over the antenna wirelessly over the radio channel. At the receiver side, we apply the reverse operation. So we first apply the carrier demodulation to extract the baseband signal from the bandpass signal. In other words, to move back from appropriate frequency band to the 0 hertz. And then we apply some series operations such as synchronization, detection, and then finally we make a decision about the transmitted bits. If it's a bit 0 or bit 1, then we reconstruct the original information. It can be text or video or image to display. So I already mentioned about this while to explain this figure. So in summary, modulation is a process of translation the baseband message signal to the bandpass signal. So, and then demodulation was the process of extracting the baseband message back from the modulated carrier. So note that this information bearing signal, they are random signal. In other words, it's non-deterministic because it changes when we transmit through the channel and so on. So as you see from this block diagram, we have a carrier modulation. Why we need carrier modulation? There are many reasons. One of the main reasons why we use carrier modulation at the physical layer is because the antenna dimension is very important, So the wavelength of the electromagnetic waves that we transmit over the antenna is related to the factor size of your mobile device. For instance, if you transmit your signal information at 3 kilohertz, you need 100 kilometer long antenna. Can you imagine such large, big antenna? That's why we use such big, antenna for the space communication, right? By NASA and so on. So that's why we use very large antennas for the space communication, since we are transmitting at very low frequency. But when it comes to the mobile device like Wi-Fi or LTE or 3G, you know, the antennas are very small that we can put into our pocket. So for instance, if you transmit your signal around 3 gigahertz, like close to Wi-Fi, and you just need a 10 centimeter long antennas. Even with some technology, we reduce this to very 1-2 centimeter level antennas, such as patch antenna and so on. So the second reason is the sharing the access to the telecom channel resources. And another reason could be to avoid the interference, because we have many different technologies: GPS, Wi-Fi, Bluetooth, 3G, LTE, and so on, radar, and so on. So if you transmit all these at the baseband level, not using carrier modulation, they will interfere. They will mix to each other. So that's why we use carrier modulation to move the information to the appropriate frequency band, because of this reason that we mentioned. Let's look at after defining the modulation process, let's look at mathematically what is modulation. So modulation can be considered as is like a multi-parameter function. F is equal to f a1, a2 up to an, and of course the t. In this case, a1 up to an, they are modulation parameters. T is the time, f is carrier. So what is modulation? Is actually to vary one or more characteristic of carrier f function in accordance with the information bearing baseband signal. In other words, if you are talking about the binary signal, according to the bit 0 or bit 1, you're going to change one of or multiple of these parameters. And we use different signal shape, such as sinusoidal, pulse train, square wave, for the carriers. Let's look at the continuous carrier modulation. As you know, when you say carrier is a sinusoid, which has A stands for amplitude, W is for the frequency, and phi is for the phase. So we have three parameters that we can adjust according to the bit stream. So if you keep the frequency and the phase constant and vary only the amplitude according to the bits, which is going to carry the information, so that is called amplitude modulation, because we are playing with the amplitude. So if it's a bit 1, we say amplitude A. If it's a bit 0, let's say amplitude 0. So that's why, because we play with the amplitude, is called amplitude modulation, AM. You know what's the AM? We use in the radio, at your car, at your home. And the other one is the frequency modulation. Now in this type of modulation, you keep the amplitude and phase constant. We just play with the frequency that is going to carry information. So in other words, you put each of your information bits on top of a different frequency. Let's say for bit 1, the frequency is going to be f1. For bit 0 is going to be f2. That's why we call it frequency modulation, FM. And this also is a popular technology that we use for the radio at your car and at your home. Another one is the phase modulation. As the name implies, we keep the amplitude and frequency constant, and we only change the phase of this sinusoid. So if for the bit 1, the phase is going to be phi 1, and for the phase 2 is going to be, for bit 0 is going to be phi 2. So by adjusting the phase, we obtain the phase modulation. In other words, we transmit information by putting each different bits on top of a different phase. And we can come up with the combination of these that we're going to see later on. So let's start with the first as an example is ASK, amplitude shift keying. This is your baseband data. It can be a text or video or image. So I'm trying to transmit 10010, which represent your information. As you see, if it's a bit 1, my amplitude is A. And if it's a bit 0, my amplitude is 0. That's why it becomes 0, 0, then 1, 0. And then on top of that, we can use pulse shaping to employ in order to remove the spectral spreading. So in performance-wise, ASK demonstrates poor performance because it can be affected by the noise, fading, as well as the interference. Because you carry information with the amplitude, and amplitude can be affected by these factors. Another second type of modulation was FM modulation, and one of the basic example for this is FSK, which stands for frequency shift keying. So assume that we are transmitting the same bit stream 1001. As you see, for the bit 1, we assign the F1, which is WC minus delta W, or for bit 0 we assign the F0 frequency. So you see the frequency of your sinusoids is changing according to the bits. So this is called FSK, and this FSK is used by standard modem that you use at your home for the internet access. And this is the basic binary FSK. We can expand this to the M-ary scheme that utilize multiple frequency as different states. And the third type of modulation was phase modulation, remember guys? And one of the basic popular example for this type of modulation is PSK, which stands for phase shift keying. Again, we are transmitting the same baseband data 1001. As you see, we assign a symbol of S1 for the bit 1 and S0 for bit 0 by changing by assigning different phase. So one of the major disadvantages of this PSK, as you see from this red circle, is the rapid amplitude change between symbols due to the phase discontinuity. And this requires infinite bandwidth. So if you want to compare this with the other type of modulation, BPSK performs better than the previous two modulation, which were ASK, amplitude shift keying, and binary FSK, phase shift keying. Similar to the previous, this is the case for the binary, only two symbols. This can be expanded to the M-ary scheme, which can employ multiple phases. That's the basic modulation. We have a different modulation technique, and one of them is called differential modulation. In the previous, so far we talked about basic modulation, which is conventional modulation, which, you know, you modulate each bit or group of bits one by one. It doesn't depend on any previous or next proceeding symbols or bits. But in differential modulation, as the name implies, it depends on the preceding bits. So in the transmitter, each symbol is modulated relative to the previous symbol and modulating signal. For instance, in BPSK, so we assign 0 when there is no change, and there is a 180-degree phase change, we assign 1. So this is the change between the current and the previous symbol. So modulation depends on the previous symbol. That's why we call differential, relative to the previous symbol. That's the transmitter part. At the receiver side, the differential modulation works as follows. The current symbol is demodulated using the previous symbol as a reference, because in order to demodulate this current symbol, you need to know the previous symbol as a reference. And the previous symbol, in this case, serves as an estimate of the channel. So if there is no change, then modulated signal to remain at the same 0 or 1 state of the previous symbol. One of the examples for differential modulation is, let's give from the phase shift keying, which is called differential phase shift keying. Differential modulation is theoretically 3 dB poorer than the coherent one, the conventional one. Why? Because the differential system has two sources of error. The first one is the corrupted symbol, and the second one, you need a previous symbol which can also be corrupted. So that's why the differential modulation is 3 dB poorer than the conventional one, since the conventional one has only one source of error, which is the corrupted symbol. In differential phase shift keying, at the transmitter side, we modulate each symbol according to the phase of immediately preceding signal element and the current data that is being transmitted. We talk about the carrier. As the name implies, we carry this information with some signals, and this carrier can be different shape. One of them is pulse. So we use a pulse, a train of pulse sometimes, to carry your text or your video or voice. And this is a train of identical pulses. As you see, they're spaced regularly in time. So this pulse carrier had different types of modulation. One of the most popular one is PAM, pulse amplitude modulation. So in this case, by playing with adjusting the amplitude of pulse shape, we assign a different bits to different pulse amplitude. And this technology is used in PBX, this telephone switching equipment that is used in usually at the offices. When you call some company, because they answer, or then you can forward to another, person. This telephone system is called PBX, and the PAM is used in this technology. Another one is the pulse duration modulation. So we assign bit 1 to one of the pulse duration, let's say T1 in terms of second, and the bit 0, another pulse shape which has a larger, let's say T2. So by playing with this, adjusting the modulation, the pulse duration, we transmit and assign the bits to the different pulse duration. Sometimes this is called PLM, which is pulse length modulation. Some people they call PWM, pulse width modulation. And this technology also is used by PBX technology. Another one is the pulse position modulation. So just changing the temporal position of the pulse, we can transmit different bits. So let's say from 0 to T1 is for the bit 1, sorry, bit 0. From T1 to T2 is position for bits 1. So if you understand that bits 0, you transmit at that specific time. If you want to transmit bit 0, you transmit at that specific position. And this is called PPM. Okay. So another process at the receiver side is called demodulation and detection. So far we talked about modulation. Okay, we modulated signal, we transmit over the antenna, it goes through the channel. Now we receive at the receiver side. How we are going to extract this information from these received signals? First of all, we apply demodulation. Demodulation simply is the process of removing the carrier signal to obtain the baseband signal. So we down convert the signal from the high frequency bandpass signal to baseband signal. This is called demodulation. After demodulation, now we need to extract the symbols, which is a group of bits, from this waveform. And we split the detection into two parts, with either coherent detection or non-coherent detection. Let's see, what's the coherent detection? First of all, for the coherent detection, we need to locally generate a replica carrier wave with the same frequency and phase at the receiver side. Once we generate this locally, we call it template signal. We're gonna, correlate with the received signal in order to detect the detect the signal. So once we detect the signal, then it's possible to reproduce or reconstruct the transmitted signal. And this is sometimes called synchronous detection. And there are different methods for the carrier recovery. One of them is pilot tone. Less power in the information bearing signal, but there is a high peak to mean error ratio problem. And another method is carrier recovery from the information signal by itself. In the first one, we send a special signal additional, which doesn't carry any information, is just for the sake of detection. We send an additional pilot signals basically, but in the second method, we don't send any kind of additional information for detection. We try to use the information signal by itself to recover the carrier. And one of the popular method in this case is Costas loop. And the coherent detection can be utilized by these PSK, FSK, ASK as well. So let's look at the non-coherent detection, which requires reference. It doesn't require any kind of template or reference signal. So because it doesn't exploit phase reference information. And that's why So in other words, it utilizes the received signal by itself to detect the signal, and this can be used by DPSK, FSK, ASK. As you see, it cannot be utilized by PSK because the phase information can be lost during the transmission. So if you were to compare the non-coherent detection with coherent detection, first of all, non-coherent detection is less complex than coherent detection because you don't need to generate any kind of template signal, but it has a worse performance. So it depends on the choice of your design requirements. Okay, let's look at the geometric representation of modulation scheme. As we mentioned, that digital modulation simply is to assign a symbol to assigning symbols to the bits, basically, or converting, mapping the bits to the symbols. In other words, you choose a particular signal Si of t from a set of S possible signals. For binary modulation, we have two cases, bit 0 and bit 1. So that's why the set of S consists of two symbols, S0, S1. So we assign the bit 1 to S1 and bit 0 to S0 symbol. So when it comes to the M-ary modulation, in this case, the signal set size is M, so that's why it's possible to transmit up to log 2 M bits per signal. For instance, if you have 8 signals, which is equal to 2 to the power of 3, if you apply the log 2, you can transmit 3 bits within a given time. In order to geometrically represent this modulation, we need some mathematical background. So first of all, any element of set S symbol can be represented as a point in vector space, and the coordinates are basis function, basis signals. So that's why they need to satisfy the following two conditions. First of all, the orthogonality, and the normalization, which is the energy is equal to 1. Then you obtain the symbols by multiplying your signal with the basis function. Let's give an example for the BPSK, which is the simplest, one of the simplest version of modulation. As you see, this set consists of two elements. This is the S1, this is the S2 for the bit duration. EB is the energy per bit, TB is the bit period. For this signal set, there is only one single basic signal, basis function, which is phi1. So that's why my first symbol is going to be square root of EB times phi1. And the next one is going to be minus square root of EB times phi1. So geometrically, it looks like this. The x-axis is the in phase, the q is the quadrature. So this plus represent the S0, which is bit 0. This minus EB represent the bit 1. And this is called constellation diagram. So in this constellation diagram, the distance between signals is very important to see the performance of the modulation. if the distance between the two constellation points are far, then the performance is going to be much better. But when they get closer, because of the noise and fading and other interference effects, the performance is going to degrade. So one of the most popular modulation types is QPSK, which stands for quadrature phase shift keying. Is simply is that two independent BPSK, one of them on the I in phase, the other is the on Q channel. So does the same performance but the twice the bandwidth efficiency. This type of modulation requires a linear amplification because of the large envelope variations, and this is due to the abrupt phase transitions. Let's look at the QPSK constellation diagram. This is one of them is like bit 00 is assigned to this S0, which is phase 0. 01 is assigned to pi over 2. 10 is assigned to, sorry, 11. 10 is assigned to pi, and 11 is assigned to 3 pi over 2. Or you can assign different, ways. Or you can shuffle this by 45 degrees, pi over 4. So with this one, 2 bits are transmitted in a single modulation symbol. Types of QPSK, because there's a main problem about this modulation was, remember, abrupt phase transition, as you see. So within a given time you can receive these symbols, and the next time you can receive this, so it's passed through the 0, so which requires 180-degree phase transition, and this requires highly linear amplifiers, which are very costly, very expensive. That's why they come up with solutions such as the offset QPSK or pi over 4 QPSK. In offset QPSK, as you see, the phase transitions are limited to 90 degree. So the transition on the I and Q channels are staggered. So that's why we don't have 0 transitions. That is going to lead to pi degree, 180 degree phase transition. In pi over 4 QPSK modulation, the set of constellation points are toggled, each symbol, so transition through 0 cannot occur. So this has the lowest envelope variations. In summary, all the QPSK modulation, as you see, require linear power amplifiers. And we have multi-level, which we call MRE phase and amplitude modulation. Such as this one, 16 QAM is one of the popular modulation. And we have, as the name implies, 16 constellation point, and the points are the distance between points can be measured by the Euclidean distance. They are close to each other, as you see, which is gonna, mess up with each other, which is gonna lead to the erroneous bits. We have 16 PSK that we position, on a circle with the fixed spacing, right? Or you can put this 16 constellation point by within 2 circles, so 8 of them are on the outer circle. The remaining 8 points are within the inner circle. So we can combine amplitude and phase shift keying to transmit several bits per symbol. In this case, 4 bits per symbol. If you are using 16 constellation point. And this also require linear amplification. That's why it's called linear linear modulation. This type of modulation are bandwidth efficient, but they are susceptible to the noise because the distance between constellation points is very small, so they can mix to each other when you try to detect the symbol at the receiver side. So compared to this, 16 QAM has the largest distance between points. So that's why it requires very linear amplification. But 16 PSK has a less stringent linearity. But has a less spacing between constellation points. Therefore, the 16 PSK is more affected by the noise. Let's look at some of these effects, the channel effects or the system effects. Assume that we are transmitting using QPSK, which has two symbols. One of the main effects is the white noise. As you see, the white noise is going to create a cloud around each constellation point. If these 2 points are close to each other, these clouds they're going to overlap, which is going to lead to the wrong detection. And we have sometimes the phase jitter effects. As you see, it can fluctuate the position of your constellation point. Also, if the constellation points are close to each other, this jitter can affect the performance of your modulation. Another popular method in terms of modulation is GMSK, Gaussian Minimum Shift Kink. This is a form of continuous phase FSK, so continuous phase FSK, in which the phase change is changed between symbols to provide a constant envelope. So the main goal is try to provide a constant envelope in this FSK. So the RF bandwidth is controlled by the Gaussian low pass filter bandwidth. That's why it's called Gaussian. The degree of filtering is expressed by multiplying the filter by 3 dB bandwidth and by the bit period of the transmission. In other words, B times T, bandwidth times bit period. So this type of modulation allows to utilize efficient class C nonlinear amplifiers so that you can lower the cost. This is called modulation spectra. You know, the Nyquist bandwidth is the minimum bandwidth that we can represent a single signal. So the spectrum, you know, this is the band that is allocated to your technology or your service. This is the yellow one. So you shouldn't overlap the neighbor channel, such as this purple or pink one, which we call adjacent channel. So you have to filter out so that your side lobes does not affect the neighbor or the adjacent channel. So in terms of bandwidth efficiency, we have the formula, which is equal to FB over the W. FB is capacity data rate, bits per second, and the W is bandwidth of the modulating baseband signal, which is equal to log 2 1 plus EB times FB over nu times W. EB is energy per bit, nu is the noise power density. So bandwidth efficiency is bit per second per hertz. Let's look at the modulation and compare these modulation types in terms of bandwidth efficiency. for the 16 PSK, the bandwidth efficiency is 4, and for the 16 QAM is 4, for 8 PSK is 3, for 4 PSK and 4 QAM is 2, and BFSK is 1, 1. And this is the error-free SNR, signal-to-noise ratio, as you see. So 16 PSK, as you see, has a 18 dB. This is 15 dB. So 16 QAM is more efficient. In addition to this bandwidth efficiency, we use also spectral efficiency for the performance of the communication systems. Let's look at the GSM digital cellular technology. The data rate is 270 kilobit per second, and we use the 200 kilohertz bandwidth in this case. So the bandwidth efficiency is equal to 207 over 200 is equal to 1.35 bits per second per hertz. How do you interpret this result? In terms of spectral efficiency, within 1 hertz, within 1 second, we can transmit 1.35 bits. Let's look at the counterpart, which is used in the North America IS digital cellular technology, is a GSM of US, basically. Data rate is 48 kilobit per second, bandwidth is 30 kilohertz, and bandwidth efficiency is 1.6 bits per second per hertz. So American GSM technology, which is IS, has a better spectral efficiency than European GSM technology, because this one you can send 1.6 bit per second per hertz. Okay, so first topic was modulation. Let's summarize. PSK is often used as it provides efficient use of RF spectrum, and we solve this by constellation point by pi over 4 degrees, and this reduces the envelope variation of the signal. And we can utilize high level, multiple level modulation, such as 64, even 256 QAM. And these are very bandwidth efficient, but more susceptible to the noise, and they require expensive linear amplification. There are some constant envelope modulation schemes, such as GMSK. This type of modulation, they require nonlinear power efficient amplifiers, which are very cheap compared to the linear amplifiers. Coherent reception provides better performance than the non-coherent, but it requires a more complex receiver. Any questions so far? All right, let's have a 10 minutes break. Minutes break. Okay, we are back. Okay, guys, any questions so far? Let's continue with the second topic, which is the diversity. So, first of all, the communication has different types of channels. We mainly split into two parts. One of them is the flat fading. The second one is the frequency selective channel. So the performance is dependent on the fading. That's why we need to increase the reliability by providing more signal paths between the transmitter and receiver. And these paths should be independent from each other. So the diversity can be provided or over time, frequency, space, code, and so on. So let's show you the diversity and the basic idea. So it's very simple. So we send the same bits over independent fading paths between the transmitter and receiver. This, of course, the independent fading paths we need to, initiate, which this can be obtained by the time, frequency, space, or polarization diversity. And at the receiver side, we combine the same, signal that we received over different paths, and we combine these different path signal to mitigate the fading effects. So as you see, in this case, we have two paths. One of them is blue, the other is the red. As you see, we are creating the diversity so that multiple paths unlikely to fade simultaneously. For instance, if the blue one is faded, but in such case, within this time, the red path can survive. Or in other words, within this time period, the red one is faded, so we may lost the bits, but in this case, the same bits can survive through this different path, which is a blue one. So we are basically creating a diversity so that we can mitigate the effects of the fading. So what's diversity then? Diversity is basically creating several independent paths between the transmitter and receiver. They must be independent, otherwise, if they are dependent, then the performance, the gain that you can get, it will degrade. So each path fades independently, as you see in the previous figure. So there's a low chance that they can fade together. So at least one of them is survived. You can obtain or reconstruct the signal, since all the signals carry the same, all the paths carry the same information. So we transmit the signal over different paths, and the receive combines this received signal for the several paths using some method. So we are going to see these combining methods shortly. So in summary, diversity is used in all mobile communication systems that we're going to see. So there are different types of diversity. We can, achieve the diversity in space, time, frequency, code. In space diversity, which is the first type of diversity, we achieve this through multiple transmit and multiple receive antennas. So at the transmitter, we have a multiple antennas, 3, 4, 5, 6, whatever. So that's why we split the power over several transmit antennas. So more antennas means more power split. At the receiver side, we have the multiple receive antenna. We collect the signal by several receive antennas. So More antennas means more collected power. But there's a condition to achieve the space diversity. In these multiple antennas, the separation, the distance between two antennas must be lambda over 2. You know, lambda is the wavelength of the signal that you use. If directional antennas are utilized, usually we prefer to have larger separation. The second type of diversity is called polarization diversity. We have two polarizations, as you know. One of them is the vertical, the other is a horizontal polarization. So transmit and receive with both vertical and horizontal polarization is achieved. So scattering is independent for each polarization so that it can lead to the independent paths. But this type of diversity is unfortunately limited to only 2x2 to transmit to receive diversity. TX polarization diversity, which means half power for each polarization. Frequency diversity, we transmit same signal with several frequencies. So the same signal over several different frequencies, F1, F2, F3. And these frequencies are separated by at least with according to the coherence bandwidth. Remember, in one of the previous lecture, we learned the coherence bandwidth, which was the channel characteristic was remaining same within this coherence bandwidth. Also, the wideband signals such as the OFDM can achieve the frequency diversity, and this OFDM is utilized in the Wi-Fi, WiMAX, LTE, and so on. We also have a multipath diversity, and in DSS, direct sequence spread spectrum, we can receive from multipaths that are separately using the rake receiver. And this diversity type is used in all CDMA 3G technologies. Time diversity, we achieve the diversity in time domain. So signal is retransmitted, or in other words, repeated after a coherence time. Remember, we learned also the coherence time of channel is the time where the channel remain unchanged. So also this can be achieved using the coding and interleaving, and it can reduce overall transmission data rates. Coding and interleaving used in all mobile communication systems. On top of that, we can also combine the time diversity with the HARQ, which is a hybrid automatic repeat request. Another type of diversity is called beam forming. So transmit with antenna array. We have multiple antenna at the transmit. We can steer this beam electronically to create a different form of beam. Each antenna in this array is fed with different phase. So you form a directional beam towards the receiver or an intended group of receiver. Antenna beam tracks the intended receiver, and this type of diversity requires knowledge of fading channel at the transmitter side, and this technology is optional in LTE 4G mobile communication systems. As you see, we have different types of diversity. The main goal in all this type of diversity is try to achieve several independent paths between transmitter and receiver. That's the main goal of the diversity. If these paths are not independent, you will experience performance degradation. More specifically, if the correlation coefficients between these paths are less than 0.5, the degradation is not noticeable. So, and since because of the limited time, we only are gonna focus on the space diversity, but most of this approach can be applied to all the other diversity methods. Okay, space diversity. To create this diversity in the space using the multiple antennas. This is called CMO, for instance, the first type. We have a single input, single transmit antenna and multiple outputs, which is the multiple antennas at the receiver side. This is called CMO. And we have a MISO. At the transmitter, we have a multiple antennas. At the receiver side, we have a only single antenna. So that's why this is called MISO. And the combination of this is called MIMO. We have a multiple antennas at transmitter and the multiple antenna at the receiver side.
So can you please give one real example to understand clearly this?
Yeah, so one example is this is the base station. We use the MISO at the base station because it's really hard to, fit multiple 3-4 antennas in the mobile device in your iPhone or Samsung smartphone. That's why at the base station, this is the base station, we can put multiple 4, 6, 7, 8. But at the receiver side, at the mobile device, we only use one single antenna because of the size limitation. Is that clear?
Yes, it's more clear. So the receiver and the sender just phones, and the middle ones are base stations.
Yeah, actually this technology can be utilized, but when it comes to practice, because of the size limitation, the CMO is used in the mobile devices, A, CMO, and the B, MISO is used in the base station. Okay, and there are some cases that we use MIMO as well, but these are not mobile devices, more like military applications.
Thank you, sir.
No problem. So that was the transmit antenna diversity. We have the receiver diversity. So as the name implies, we signal from the multiple receiver antennas are collected and we need to combine them. So this is one path that we collect, this is another path that we collect, and so on. M path. And we multiply with the weight, optimal weight. Each branch has a weight which is complex number. And then we align the faces, and then we combine this constructively, coherently. So in this case, the receiver must estimate the phase of each branch, and the estimation, we achieve this estimation through the pilot signals. So there are multiple ways to collect and combine these different signal that we obtain from the different paths. So one of them is called selection combining, the other is threshold, maximum ratio combining, equal gain combining, and the combination of these above. Each of these combining technique has some pros and cons. So there's a trade-off between performance and complexity among these techniques. Let's summarize shortly these combining techniques. In the selection combining, we just select, we receive from the multiple paths, we only select and use the path that has a highest gain. We ignore the others. That's why it's called selection combining. The other one is the maximum ratio combining. This is the optimal solution. All the paths, they are co-phased, aligned, and then we multiply with the optimal weight so that we can maximize the output SNR. This is the optimal solution. The other one is equal gain combining. Similarly, all the paths, they are co-phased, aligned, but we multiply with the equal gain for each path. But in the maximum ratio combining, we find the optimal weight for each of them, which is more complex. We have array diversity gain. Array gain is from the noise averaging. and the diversity gain is change in bit error rate slope. Okay, this is the MIMO case. So traditional diversity is based on multiple receiver antennas, but MIMO is based on both transmit and receive diversity. This is also known as STC, space-time coding. In this case, we have MT time transmission antenna, MR receiver antennas. So in this case, we may have M times MR branches. So the TX and RX processing, as you see in the figure, is performed over the space as well as the time. So as the name implies, we need multiple antennas at the transmitter and multiple at the receiver side, but it's difficult to put many antennas in the mobile devices, as you know. That's why diversity in the downlink is used for the MISO, because we can fit many base antennas in the base station. In the uplink from your mobile device, your smartphone, to the base station, we use uplink diversity, which is a CMO. So this diversity is achieved by the conventional diversity, which is a single input, multiple outputs. So therefore, all the diversity cost is moved to the base station, because base station is a big, large, there's no space problem. But in the mobile smartphone, we have a space problem. That's why we use CMO at the mobile, and we use the MISO at the base station. And all 3G, 4G, 5G, they utilize this MIMO technology. We have different types of MIMO technology. Two major types of space-time coding is space-time block coding, STBC, space-time trellis coding, STTC. STBC is simpler than the second one, and it can provide better performance. And STBC is used in mobile communication. STTC is not used in any systems because of complexity. Let's look at the space-time block code that is utilized in mobile communication. There are a few major types. One of them is the transmit diversity. The goal in this case is to achieve the diversity gain. We have a spatial multiplexing. The goal is to increase the data rate. We have eigensteering. The goal is both of above, to achieve the diversity gain as well as increasing the data rate. But this requires knowledge of channel at the TX side. And we have the mix of above, still is a research topic that is ongoing. And the above three diversity STBC methods are used in mobile communication standards. So let's look at the transmit diversity. In this case, the simple case is two antenna at the transmitter and one antenna at the receiver side. So we have two symbols, S0 for bit 0, S1 is for bit 1, are transmitted over two transmission period. We have two transmission period. No change in the data rate. As you see, it has some mathematical background that I'm skipping. So you multiply and do some processing at the receiver side. This is the spatial multiplexing, also how to receive 4 copies, as you see, through 4 different paths. In the spatial multiplexing, the main goal is to increase the data rate by 4. This 4 channel gain must be known at the receiver. And how do we achieve at the receiver side is using this zero forcing algorithm. That was about the diversity. Now we are ready to talk about the last topic, which is direct sequence spread spectrum. This is all technology that is being used in military communication. So in many military communication, we use this spread spectrum because of the secure communication. So it's as simple. Instead of sending this symbol S of t, we multiply with the bit sequence. This is a kind of a secret code that it's known by the transmitter and receiver. Nobody else can, decode this signal unless they know this chip sequence. So when you multiply with the chip sequence, actually we are spreading the bandwidth by factor of k. So that was blue one was my original S of f. After multiplying with this code, special secret code, I spread the bandwidth of my signal. So let's say my original was 10 megahertz, and I did with the 8-bit sequence, chip sequence, then I spread to 80 megahertz. So that's why it's called spread spectrum. You're spreading your bandwidth. We're using a secret code. At the receiver side, you despread by multiplying with the same secret code. If you don't know this secret code, you cannot decode this signal. This is also popular because it mitigates the inter-symbol interference, and also any kind of jamming or interference. If someone is jam your signal or attacking your signal, this is very powerful technology to mitigate these effects. How this ISI and interference rejection happen? Let's say this is the information signal, blue one. I multiply with the secret code SCF, and I spreaded my signal, as you see in the frequency. And someone, my enemy, jammed my signal, which is the red one. And as you see, it can only jam a limited bandwidth, this region. So that's fine. So at the receiver side, when I multiply with the secret code, as you see, I'm kind of spreading the enemy's interference signal. It makes like a noise, but on the other hand, my original signal is sticking out. So at the receiver side, when I multiply with the secret code, my original signal is sticking out, and the interference, the jamming signal is removed. So with one process, I'm, sticking out my information signal and removing the interference signal. So we utilize the same technology for the multipath rejection. As you see, this is my blue first path, and the red one is the second path. So when I multiply with the same gain, my intended path is sticking out, and the second path is disparate. This technology originally developed for the military application, but later on it's utilized by the CDMA, which is the core technology for 3G. So the main idea here, I assign a unique code to each mobile user. User 1, user 2 coding, user 3. And of course, these codes has some conditions, some requirements. They have to be orthogonal as well as normal, so which is called orthonormal. So CDMA uses these unique spreading codes to spread the baseband before the transmission. Then the signal is transmitted in a channel which is below noise level. So you see there is no signal actually. It's below the signal. You embed to the noise basically. You camouflage your signal basically. Then the receiver uses a correlator to disparate wanted signal, which is passed through the narrowband pass filter. The unwanted signals will not be disparate, So that's why they are removed. We have another big problem in the mobile communication system, which is the intersymbol interference. So simply, I transmit my signal within this duration, bit duration, but because the channel can spread, can leak to the blue, green, even the the black one. This is called intersymbol interference. So it should stop here, but channel effects, it can spread your signal, which is gonna mix all these symbols overlap to each other, because it's gonna create a problem at the receiver side when you detect and demodulate this signal. So ISI happens when the symbol duration is much greater than maximum delay spread of the channel. So one of the sorry, one of the solution is to use equalization. So because this ISI happened due to the channel, and channel behave like a band limited filters, as you see. Equalizer is just a, you can think like a is an equalizer effectively invert the channel. So you undo the effects of the channel. That's called equalizer. But this equalizer has some poor performance, especially when the frequency selective channel is experienced. Another solution for the ISI, which is the popular solution, is to use OFDM. So if your symbol duration is much greater than maximum delay spread of the channel, then you just send a large number of narrowband carriers. So instead of sending the whole band, we split the channel into the sub narrowband channel. That's why each is going to have a R over M. So that's why my symbol duration is going to have TS times M. So as if I am increasing my symbol duration to the M symbol duration. That's why I'm satisfying this TS greater than TM, and then I reduce the effect of the ISI. This is how we do achieve OFDM, by splitting the whole channel into the sub channel. As you see in this case is 10 sub channel, and then 50% bandwidth saving can achieve, and this is done through the FFT, or discrete Fourier transform. And that's all for today. Any question?
Sir, can you compare CDMA and OFPM again? What is the plus and minus?
So first of all, CDMA is like an apple and OFDM is an orange, so we cannot compare. It's a different technology. CDMA is a multiple access technology. So we have a multiple user that wants to access to the resources, right? Multiple access. So the base station, I'm the base station, 3G base station, and you're at the university. We have how many? Let's say 10 students. One of them is using YouTube, the other is looking at Facebook, the other is doing WhatsApp, and so on. Each of you guys are doing different applications, right? So that's why I assign at each of you a unique code, and these codes are orthogonal to each other. So when you request a YouTube video from me, or WhatsApp server or Facebook server and so on, I multiply your signal, your YouTube video, with your code, and the other student WhatsApp text with another code, and the Facebook image with another code, and then I combine all together and transmit to all of you guys. Actually, you receiving all the information of the other students. But how you're gonna only extract your YouTube video, when you multiply your unique code, you're gonna obtain, stick out your information, and you're gonna cancel the other student information because of the orthogonality. Is it clear? OFDM, it solved the problem of this intersymbol interference. So when I send a transmit signal within this time, I should only get within this time. But because of the channel, it's gonna spread my signal over and leak to the other symbols, even to the blue and green one. So this is gonna mix all the symbols, all the bits. So how the OFDM solve this problem is increase the symbol duration. How does it increase the symbol duration? It was from here to here. Now it becomes symbol duration comes up to here. So when you increase the symbol duration, your channel effects is gonna remain within this symbol duration. So simply OFDM increase your symbol duration so that this leakage, this interference between the symbols cannot happen. Is it clear?
Clear, sir. Thank you.
All right. Any other question? Thank you, guys, and I'll see you next week. Take care.
Take care.